those results.
Absolutely. Let's get those TLC plates up and see what the data tells us. All right, let's crack open this worksheet and see what the scientists found. We have 2 TLC plates, one for amino acids and one for oxo acids, each with spots corresponding to the different incubation tubes.
I see some labels here. Alanine, glutamate, pyruvate, oxoglutarate. Are those the controls?
Exactly. Those are our reference points, like a molecular ruler, helping us identify the positions of known molecules on the TLC plates. It ensures we can accurately interpret the results.
That makes sense.
Yeah.
Okay, so let's walk through the results tube by tube, starting with the transamination reactions. What jumps out at you?
Let's begin with tube 1, our negative control. It contained only pyruvate and the heart muscle extract. No spots appeared on the amino acid plate, which is what we'd expect. Transamination requires both an amino acid and a keto acid to occur.
So tube 1 confirms that we need all the players present for the reaction to take place. Now I'm looking at tube 5, which also contained a pyruvate, but was treated with DNPH for the oxoacid plate. I see a yellow spot.
That's our pyruvate control, giving us a clear reference point on the oxoacid plate. Now compare that to tube 7, which included both pyruvate and glutamate. Notice anything different?
Whoa! There are 2 spots on the oxoacid plate for tube 7. One matches our pyruvate control, and there's a new one further down. Is that the 2-oxoglutarate we were expecting?
You nailed it. That second spot confirms that transamination took place. The amino group from glutamate was transferred to pyruvate, forming alanine and 2-oxoglutarate.
Seeing that new spot appear really brings the concept of transamination to life. And I bet we see evidence of the newly formed alanine on the amino acid plate.
Right. Let's look at tube 3, which had the same reactants as tube 7, but was stained for amino acids.
I see 2 spots. One lines up with the glutamate control, and there's a second one. That must be the alanine.
Precisely. Tubes 3 and 7 are showcasing the same transamination reaction, but visualized from different perspectives.
Yeah.
It's a beautiful example of how scientists use different techniques to confirm their findings.
Okay, so we've confirmed transamination. Now let's move on to deamination. What were the key observations there?
Tube 4 contained glutamate and NAD+, the essential components for deamination. However, we don't see a new spot on the amino acid plate. That might seem counterintuitive at first, but remember...
Right, deamination removes the amino group. The product is an oxoacid, so it wouldn't show up on that particular plate. We need to check the oxoacid plate for tube 8, which used the same reactants.
Excellent deduction, and there it is. A new spot matching 2-oxoglutarate, the product of glutamate deamination.
I'm noticing that some of the oxoacid spots look a bit irregular. Is that normal?
Good observation. Some oxoacids, like pyruvate, can exist in slightly different structural forms called isomers. These isomers can separate into 2 spots on the TLC plate during the process.
Ah, so it's not a mistake, just a quirk of these molecules. And what about that faint spot near the top of the plate?
That's simply the unreacted DNPH, the staining agent itself. It's not always perfectly neat, but we can focus on those distinct spots that reveal the story of transamination and deamination.
This is incredible. We've gone from theoretical concepts to visual confirmation of those reactions. But I'm curious, how does all of this connect to the broader metabolic picture?
That's the crucial question. We've seen the mechanics, but now we need to understand the significance. And that, my friend, is where we'll pick up in part 3.